Good morning, all the people that watch my channel, whoever they are. I'd love some comments sometime, but I mean, keep it polite, etc. I know I go off the wall, so I'm prepared. Today, let's talk about the Weyl Dirac Large numbers, and I put the Weyl there because apparently, Weyl thought of it first, and Dirac got obsessed with it and got famous for his obsession with it. But I want to look at how this plays into neutron decay cosmology. So, in neutron decay cosmology, we'll start over here. We have a mass unit, which is a photon of 2 pi Planck length, wavelength, trapped over its own gravity. You can do the math. I put up a link to some guy that asked the question and did some elementary math. Anyways, but this is the premise. Because very simply, it's like, well, if you have a Planck length, then the circumference will be 2 pi Planck length, or half the circumference will be 2 pi Planck length. The diameter would be. So therefore, you could fit a photon around the circumference of such a shape. And that would be, in theory, the smallest shape. Some people will say, oh, Planck lengths don't matter. Unsicher is like, if anybody mentions Planck, you should go running, so you should run now. But this is the premise of neutron decay cosmology. You have this mass unit. Because this mass unit creates a convergence in space because gravity, and here's like a little gravity well thing. Ooh. Very simple premises. Okay, because we're imagining space as sort of like a fluidic or a single sheet of stretchy rubber. A single sheet of stretchy rubber. You constrict one place, that means you have to stretch out another place because it all used to be just infinity kind of at the cosmological constant. So, or some density. So we have this gravity at the proton. We have a convergence of space, which creates the positive charge. And we have a divergence over here, compensatory, which creates the negative charge. There we go. Okay, this is the premise. That basically there's a proton here because of this positive charge, and the electron is the compensation to balance out this proton. So out here, let's say, so right now we have a hydrogen atom, we have a neutron, or the photons fell apart, the negative went outside, being expansive, divergent. The positive is the middle because that's convergent, and together they balance out to nothing, right? The whole idea is that this is now an enclosed thing. The proton has no influence out here anymore. The proton has some influence here because there still needs to be some electron. But at a certain point, basically, it achieves balance, where this is now a contained unit. There's not a defined line, it's a little vague here, as everything tends to be. It flows, and therefore not a straight line, but this is the premise. It's that the outflow, or the inflow, which is divergent, the inflow of the electron flows into the outflow of the proton. The mass of this unit creates this whole situation. Now, there we go. So that's the first part. Now, here's our universe. Observable universe limit. With Dirac, he used time, but that was as Gamow pointed out, you shouldn't use time because that is then already assuming this characteristic, which Gamow didn't necessarily ascribe to, nor Weyl, that this expanding universe idea, that instead the Doppler shift is a geometric issue, which I'll address in another video, or I have addressed, but I'll address again, that this is a geometric curvature, which we necessarily don't see. We see it as flat space, but that's not necessarily the way we measure our flat space is about distribution, not about an additional component, which dark matter might even be through Mond. Anyways, main point, limit of observable universe, mass of universe. These things are proportional. This is a microcosm. The hydrogen atom is a microcosm of the same thing. The gravitational constant creates a curvature of space which limits our ability to see beyond it. The mass of the universe related to the size of the universe is proportional to the mass of the electron, and the size of the mass of a proton, electron hardly counts, mass of the proton relative to the electron orbital. This is the mass of the universe. Yes, it's more distributed, and instead of having very singular charges where there's the proton and there's the inflow, instead what we have is a whole bunch of these with their own little charge units. This is not a charge thing. I'm not proposing this is some electrostatic universe. I believe plasma is super important to the universe, but I do not believe that electrostatic forces, like gravity is not electrostatic force directly. Otherwise, what, you change somebody's charge, and you can change their weight a bit, but I mean, you can't just completely negate gravity by having a neutral charge. That's a misconception about charges. This is the Dirac Large numbers, that the mass of the universe is proportional to the size of the universe, the same way that the mass is proportional to the electric charge, and therefore the curvature created in space by this electric charge. Yeah, super cursory. You can look it up more. But fundamentally, this is what I think is the way it goes. Like, this is the hydrogen atom. It's very simplistic, but it tells us everything we need to know about the way the universe works. A neutron decays into a hydrogen atom. This is well known, though at the same time it's sort of negated as a fact. It's like, well, it doesn't usually happen in our circumstances. Yeah, that's because our circumstances are not deep space where there's absolutely nothing else. Okay, we have a lot of mitigating factors. We have all this energy from the sun. We're living in a very complicated dynamic here on Earth. But in deep space, the math says neutron decays into hydrogen and shoots out a neutrino at the same time, which will be used later to turn that hydrogen back into a neutron. And this is the Dirac large numbers, put in a super tiny little nutshell. The proportionality of the mass of the universe to the radius of the universe, not the age of the universe, the radius of the universe. To say it's the age of the universe is presumptuous. That's already saying that you're correct in this theory. What we know, or what we have a better idea of, is that it's the radius of the universe. And it's still a pretty guessy thing, but from the observed curvature of the redshift, blue, red, if it was flat, it would be red because there would be no oscillations. Blue or whatever is basically like where the observer is, there's no adjustment. As you go further and further away, things get dragged out until they will seem flat at the point where they are so low, so slow that we can't detect them anymore, is the limits of observability. Now, whether that ever stops or not, we'll have to build bigger and bigger things and do more and more radio telescope and work our way down the entire spectrum. And is there a limit? Is there a true limit for where we get signals? Is there absolute distance for signals? Or does everything just get shifted and shifted and shifted forever? Is it a parabola or is it contained? This is the real question. But the Dirac large numbers is this proportionality. The charge relative to the mass is equal to the radius relative to the mass. That's it. Thanks. Bye.